Welcome back to this class. So in previous classes, we were studying about this encoder, decoder, and in encoder, specifically priority encoder. Today we shall learn about multiplexer. So what it is multiplexer? So multiplexer is a combinational circuit that selects binary information from one of many input lines and directs it to a single output lines. It means, suppose this is a block diagram of mux, that is the multiplexer. So there are many inputs and one output. So these are the input and this is one output. So from many to one, that is called multiplexer. More specifically, in binary, there are 2 to power n input lines, maybe sometimes lesser than, but most of the time 2 to power n input lines and one output lines. So out of these 2 to power n input lines, suppose n is equal to here 2. So total input lines will be 2 to power 2 will be 4. So 4 input lines. So out of these 4 input lines, one line be selected and given a path or connection to the output lines. So this is what is there. The selection of a particular input line is controlled by a set of selection line. So this will be a selection line. Suppose n is equal to 2. So n number of selection line. N is equal to here selection lines. So now this is the relation between input, output and selection line. So number of input 2 to power n, output always 1 and selection line n. Okay. So we shall try to further see how it's working. So a 2 to 1 line, that is 2 cross 1 line, multiplexer connects one of the two 1-bit sources to a common destination. As shown in figure 4.24, let us see what it is. 4.24, yes, this is the diagram. 4.24 and 2 to 1 line multiplexer, or in simple term, we can tell it is a 2 cross 1 mux. So as we can see, number of input is equal to 2, output is equal to 1 and number of selection line will be, so we can write 2 to power n is equal to here 2. So what should be here? And should be 1. So that will be number of selection line. So that is why s is 1 here. So further looking here, yeah. So number of selection line 1, output is 1, and number of input lines 2. So what are those two input lines? I0 and I1. These are the two input lines, which is written here as a block diagram. And selection line is only 1, and this is the output. So this is the input, this is the selection line, SELE, selection lines. So we have labeled the input. So input 0, input 1. So this is not a logic, only this is the numbering. This number 1 input, number 2 input, you can say. Okay. And this is the output, and this is the selection line. But what is inside this box? Inside the box for say 2 cross 1 multiplexer is this diagram. Okay. And this diagram you can say this is again AND OR structure. Okay. So AND OR structure is conducted in particular fashion. You can see here AND gate 1 and gate 2, and say this is OR gate. 3 gates are required. Let us see how output is selected, particular output. Since it has 2 input, so which at the output, what shall be the expression? So it is controlled by selection line. So if S is equal to 0, suppose S is equal to logic 0, this is one case. In another case, S is equal to 1. These are the only two things which it can take the value S is equal to 0 and S is equal to 1. So consider first S is equal to 0. If S is equal to 0, then what will happen? The 0 will come here at the second AND gate, and output of the second AND gate will be simply 0. Why? Because anything coming here at I1, whether it is 0 or 1, output will be 0. Why? Because one of the input is 0, and 0 multiplied by anything will be 0. Now since this is here 0, but here it is not gate, so as output will be here 1. And this 1 output of this NOT gate is connected to the input of first the AND gate. So here it will be 1 in case of S is equal to 0, and whatever input is here available, it should be here I0. If I0 will be 0, then output will be 0. If I0 is equal to 1, output will be 1. And then in the case, the output will be I0. When? Now I can write here, when S is equal to 0, then output is equal to I1. This is the first case. It means when S is equal to 0, this input was selected and available at the output line. Now, second case. If S is equal to 1, then what will happen? If S is equal to 1, this 1 is coming here at this second AND gate. I will change the color here. This is this is 1 here. It means this AND gate will be enabled basically, and whatever I1 is here, I1 will be available here. And since it is 1, then next time it will be here 0. Next time is in the same way, because this is not gate, and this 0 makes AND here this disabled. Okay, so output will be here 0. So when S is equal to 1, you can see I1 is coming here. 0 plus I1 will be I1. So what is the in nutshell? When S is equal to 0, then Y was I0. When S0 is equal to, no, S, it is not 0 as such. S is equal to 1, then it is I1. What I mean to say, when S is equal to 0, then first, and S is equal to 1, then second input is selected and available at the output. So this is the description of the circuit. Let us see what is, the same thing is written here. The circuit has two data input lines. We have seen this I0 and I1. One output line, okay, that is the Y, and one selection line, that is the S. When S equal to 0, the upper AND gate is enabled and I0 has a path to the output. When S is equal to 1, the lower AND gate is enabled and I has a path to the output. The multiplexer acts like an electronic switch that selects one of the two sources. The block diagram of a multiplexer is sometimes depicted by a wedge-shaped symbol, that is, okay, exactly it is there, but we used to sometimes show like that only, one output and many input. Okay, wedge-shaped symbol as shown in figure 4.24b. It suggests visually how a selected one of the multiplex data sources directed into a single destination. The multiplexer often labeled as a mux. Okay, anything? Yeah. Now we will come to next. This is the simplest one, that is the 2x1 multiplexer. Similarly, we can go for the 4x1 multiplexer. I hope this image is visible. If you can see, this is a 4x1 multiplexer, that is the mux. 4x1 means number of inputs are 4. That is a label, it has been labeled like this: I0, I1, I2, I3. These are the 4 inputs. How many outputs? Only 1. So if number of inputs are 4, so if I will tell like here 4, so what is the value of n? and will be here 2. Okay, because 2 to power 2 is equal to 4. So and this n is equal to 2 is number of selection line. Number of selection lines. And what are those selection lines? It is labeled here S0, S1. These are the selection lines. These are the input and these are the output. So if I draw a block diagram of 4 cross 1 multiplexer I0, I1, I2, I3, this is inputs and one output and two selection line S0, S1. So this is the block diagram of 4 cross 1 multiplexer. Okay, but what is the inside of this block? This is the circuit. Okay, inside the circuit, it's like that. So same way we can understand the functional table of this multiplexer. Like here, selection line S0 and since now 2-bit selection line n is equal to 2, so total 4 positions it will take, like 0 0 0 1 1 0 1 1. And when 0 0 is selected, you can see y will be I0. This first line will be available here. If 0 1 is selected, then I1 will be selected, second one. The rest will be disabled. Okay, 1 2 3 4 and gate. So first AND gate will be enabled when S0 and S1 both are 0 0, and rest all will be disabled. In case of 0 1, second AND gate will be enabled and rest other AND gate will be disabled. That is why I1 will be available at the output y is equal to I1 when 0 1 is selected. Similarly for 1 0 I2 and 1 1 I3. So we can visualize the way the circuit is connected in that way only, just to make enable and disable particular NAND gate. So with this, I think what is this? Okay, sometimes entire circuit we want to what is called control. Then what enable line is given here when E is equal to 1. So irrespective of the selection line, all will be zeros. And when E is equal to 1, this then based on the selection line like S0 or S1, the particular input line is uh, enabled and will be available at the output. I think this circuit is quadruple. Quadruple means 4. So there are 4 number of 2 cross 1 multiplexer. 2 cross 1 mux. But how many total? They are total 4. 4 in number. 4 in numbers. So this is the diagram of what is called quadruple multiplexer. Now let us see how to realize a Boolean function with the help of multiplexer. Once we understand the multiplex in the circuit diagram, we can see multiplexer is nothing but the implementation of AND logic and OR logic. Okay, and it has many input and many output. We should know the relationship because we have studied this decoder, encoder, and now third one is the multiplexer. So in decoder, so let us begin from here. Multiplexer, 2 to power n input line, n selection line, 1 output line. In decoder, we were having an input line, 2 to power n output lines. So like 3 to 8 decoder. Okay, and reverse of decoder is the encoder. It means we will have say 2 to power n input line and n number of output line. Okay, like octal to binary decoder or something like that. This kind of thing we have studied, and more specifically as an example, priority encoder. So we can see what is the relationship between input and output as far as decoder, encoder, and multiplexers are concerned. And these decoders are used for realizing the circuit. What kind of circuit? Like full adder, half adder, etc. Encoder is specifically used for priority encoding things, and multiplexer can also be used for implementing logic function. So let us see how it has been used to implement a logic function. So example is given. Suppose a function f, which is function of x, y, z, having is equal to summation 1, 2, 4, 6. It means at these midterms, f is equal to 1. Okay. So let us see what is given here. 2. Okay. So first task is that to decide how many, what shall be the size of multiplexer to be used for realization of this function. Okay. So size, how to determine the size? We can see when we observe this function, we can see this is a 3 variable function. So n is equal to here 3. So 2 to power 3 will be 8. So 8 number of possible combinations are there. We can see from here also, like 1, 2, 6, 7. It means up to 7. 7 inputs are available here. So what shall be the size of multiplexer to use for realizing this Boolean expression? That shall be 8 cross 1 multiplexer. 8 cross 1 multiplexer. I will draw here. You can understand it is not going to be very difficult task. Just, are you able to see class?
Yes, sir.
Yes, sir.
So this is your 8 cross 1 multiplexer. 8 cross 1. 8 cross 1 means what is the output and 8 number of input. So I will write like here 0, 1, 2, 3, 4, 5, 6, and 7. So these are the input like I0, I1, I2, I3, I4, I5, I6, I7. And we will have how many selection line? 3 selection line. Okay. And what are those 3 selection line? These are X, Y, Z. Okay. These are the selection line. And this X, Y, Z will take what position? Total 8. Like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. These are the all 8 combinations which this selection line can take. Now, if 0, 0, 0 is there, 0, 0, 0 is there, so y will be what? As per this function, y or this f is equal to f is what is this summation 1, 2, 6, 7. Y should be 0 because at 0 there is no output 1. Okay, so this 0th one we will give logic 0. We can connect with logic low. Okay, low potential. However, when this x, y, z is equal to 0, 0, 1, then you can see f gives 1, logic 1. So this will be connected, I will put here below. Let me change the color. Okay. So this is, here I am giving logic 1. Logic 1 means plus 5 voltage here, and logic 0 means 0 voltage. Now these two occurs. Now 0, 1, 0. 0, 1, 0 means 2. So to add 2 also it is logic 1. So let us connect this logic 1. And next 3, no 3 is 0. So we have to put 3, 1 with logic 0 here. 4 again same thing, 5. But 6 and 7 both are logic 1. Okay, so we have to connect 6 and 7 with this. So that implementation is over. Got it? So you just connect whatever functions are given here to logic 1 and rest logic 0. So in this way, you are able to realize a given Boolean function with the help of 8 cross 1 box. Okay? See, here we have to see one thing. Suppose I ask design a full adder with the help of multiplexer. So in multiplexer, let me see. Yeah, it is not there. Uh, I write here. Suppose question: design a full adder with the help of multiplexers. Okay. So we know, suppose I take x, y, z as an input 0, 0, 0, 2, 1, 1, 1, and the outputs are sum and carry. These are the two outputs. So we used to write the expressions here. Expression means here what is called this Boolean expression. So S will be something. Similarly, carry will be also here something. So now, since in multiplexer only one output is possible, so in order to implement this full adder with the help of multiplexer, so we need two multiplexers. One multiplexer will give sum as an output, and another multiplexer will give carry as an output. Okay. So this is in this way you can see here whatever rightly from the truth table, right from the truth table, you can realize the circuit. No need to simplify the Boolean expressions. Why? Because in multiplexer all kind of combinations input are available. Okay. So this is the advantage of using multiplexer. So multiplexer becomes a generalized circuit, a ready-made circuit which you can externally programmed. It is a kind of hardware program. Okay. So this is the thing. Now another example they have given here. Yeah. For variable f is a function of a b c d and summation 1 3 4 11 12 13 14 15. So here issue is that suppose see straightforward you can see this function requires 16 cross 1 multiplexer. Okay, so if you have 16 cross 1 multiplexer there shall be no issue. Okay, but if we have suppose 8 cross 1 multiplexer only and given function is like this, then how to realize? If here they have given 4 cross 1 multiplexer, but you have to realize this 8 cross 1 multiplexer function. 8 cross 1 multiplexer you have to realize with the help of 4 cross 1 multiplexer. So how to do this? Size is Boolean function require larger size, but hardware available is lesser size. So how to realize that kind of thing you can see from here. I think let us see this 4 cross 1. So what was the function? Function is equal to here this 1267 1267 1267. So you can see this is 0 1 2 3 4 5 6 7. All 8 combinations are available as a function of x y z, and you can see here f is 1 at 1, f is 1 as 2, this is 2, f is 1 as 6, this is 6, f is 1 at 7. Okay. Now what we are trying to do, suppose we want to implement this 8 cross 1 size of function which can be done straight forward the way I have implemented here. But issue is that suppose instead of this 8 cross 1, we have 4 cross 1 multiplexer. Then how to do? That becomes a problem. So that problem is going to solve here. So we have written all 8 combination as an input and now write the function. So function we have also written like 0 at 0, output is 0 at 1, 1. Now try to take one of the variable as a input. So here Z has been considered as an input. Z has been considered as an input. Okay. So now selection line will be XY. Selection line will be only xy. These are the two selection line, and z is the input. Okay, so z is considered as an input. So if two-bit selection line is there, then we have obviously four input lines, because 2 power 2 is equal to 4. So, and we give the we labeled basically these inputs like 0, 1, 2, 3. But 0, 1, 2, 3 at these, what is the input? Whether logic 1 or logic 0, that is the question. So let us see how this has been formulated. Suppose both are 0, 0, that is the x and y, both are 0, 0, and this is the condition where both are 0, 0. Okay, I will take red. Both are 0, 0. These selection lines are 0, 0. And you can see f, you look at f is equal to 1. If f is equal to 1, then what is the status of z? What is the status of z? So you can see z is equal to 1. Okay, so it means this is z, not z bar. Z bar is this 0. So f is equal to 1. So this is a z. So that is why f is equal to z. So whenever x and y both are 0, 0, that is the first place, you can see input is given simply z. Got it? Next, let us see next one, then you will understand more. So now coming to next number is first is 0, 0, second one is the 0, 1. So you can see x and y both are 0, 0, 1 here. Okay, and now that is the 2 and 3. And 2 and 3, what is the f? F is equal to what? When z is 0, that is the z bar. It means at 1 we have to write here z bar. Okay, that is what is written here. Now you see z is now as an input line. So z bar. Now go to 1, 0. 1, 0, that is the xy. So 1, 0 is here. So you can see at both f is equal to 0 for both cases. So that is why f is equal to 0. So at 2, that is this place, we have given logic 0. And when f is equal to 1, the 1, 1, let us see for this. So 1, 1 is here. X and y both are 1, 1 here. So you can see z f is equal to 1 when z was 0, as well as f is equal to 1 when z is 1. So on both cases, so simply we can write here f is equal to 1 with confidence, the way we have written here f is equal to 0 for both cases irrespective of the z. So that is why 0 and 1. So at 2 and 3 respectively, 0 and 1 can be written. So what is the conclusion? Conclusion is that the function which otherwise was able to implemented with the help of larger size of multiplexer, that is the 8 cross 1, now we are able to implement with the help of 4 cross 1 multiplexer by considering one of the input, one of the selection line as an input. In this case, it is Z. Any question? So this is the advantage of learning how to realize higher side of multiplexer. Same goes with this another question. This is f is equal to a b c d 1 3 4 11 12 13 14 15. So you can write here f is equal to this function. Okay, what? Let me see. 1 3 4 11. 1 3 4 11. Next 1 3 4 11. 12 13 14 15. 12 13 14 and 15. So at these positions f is equal to 1. So let me little bit reduce the size. So we have written four, since it is a what is called this total number of inputs or midterms are 16 from 0 to 15. It means total will be 16. So 2 to power n is equal to 16. So n will be here 4, and it is written here also. can see f is a function of a, b, c, d. So that simply says your selection line. So in simple case, we can realize this function with the help of 16 cross 1 multiplexer, straightforward. But no, we are not going to do like this. We are going to implement this function instead of 16 cross 1. We want to implement with the help of 8 cross 1 multiplexer. Okay. So how can we do? Same principle we have to apply here. So let us see here A, B, C as an input. No, sorry. A, B, C as a selection line and D as a input. D is a input and A, B, C as a selection line. Now selection line is 3-bit. So 3-bit number will go from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Total 8. Okay. And these are the number. Like first one, I will write down this what is called decimal number 0, 1, 2, 3, 4, 5, 6, and 7. This is 1, 1, 1. And this is the D is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is the pattern you can observe. And what is the F for each case? Like from 0 for 0, F is equal to 1 when D is 1. So that is why F is equal to D. Here again same. Here F is equal to 1 when D is 0. That is the F is equal to D prime or D bar. And here both cases 0. Here also 0. At this same thing, when f is equal to 1, d is equal to 1. So f is equal to d. Similarly here, both are 1, 1 irrespective of d. So f is equal to 1. And at that place, again same thing. F is equal to 1 for both cases. That is why 1. Now simply, since it is now total 8, like 0, 1, 2, 3, 4, 5, 6, 7. These are the input. And this is the selection line. 3 selection line A, B, C. 1 output line, and here we have to give the inputs. So when S0, S1, S2, both all are 0, 0, 0, that is the first number will be selected. And first is what? First is this 0, 1 is 0 is equal to D. So we have to write here D. Then for 1 also D. Then 2 is equal to D bar. So that is why D is connected with NOT gate and D bar is available here. And next is the 0. So third and fourth both are 0. And then fifth is okay. One is also fifth one is also D. So that is why it is connected here. Fifth one is connected with D. Sixth and seventh both are 1, 1. So one is connected to 6 and 7. And your circuit is implemented. So whatever arbitrary function is given like here, you can realize with the help of multiplexer either directly, or if it is told that okay, implement with the lesser size of it, this way we can do. So just hold on.